We have just defined our image restoration process, and we have seen that it boils down to a minimization problem. In this section, we shall try solving it using classical optimization tools. This is our minimization task. It is a convex problem, and thus we are free from the fear of local minima points. The first thing I would like to do is to discuss the involved dimensions. We will be working with an image of size 256 by 256 pixels, and thus D has about 65,000 rows. Since it is 10 times redundant, it has 650,000 columns, and this is also the length of our unknown alpha. The Blair operator H is a square matrix of size 65,000 by 65,000. Note that we need not hold D nor H as explicit matrices. Instead, whenever we need to multiply by these matrices or their transpose versions, we apply them as convolutional filters. Now that we understand our mission better, we need to find relevant algorithms for handling it. The literature in optimization theory is quite rich, and there are various options in front of us. More specifically, here are a few options we could consider, starting from the steepest descent through the conjugate gradient and going all the way to more sophisticated and more complex methods such as interior point algorithms and more. We will focus on the first two due to their simplicity. Let's talk about the steepest descent, SD for short. We denote the function we are about to minimize as f of alpha. The SD algorithm relies on the gradient of this function, which defines the direction of the maximal ascent in this function, so here it is. Note that when taking the derivative of L1, we get the sine function. Here is the iteration formula for the SD. In each iteration, we simply walk in a direction opposing the gradient, so as to get the maximal descent. Plugging in the gradient formula, we get this iterative equation. The parameter mu is the step size to take, and a careless choice of it may lead to divergence. A good value to use depends on the maximal eigenvalue of the Hessian, the second derivative of f of alpha. We shall use this approximation later on to find a proper value for mu. A brilliant trick in optimization is momentum acceleration. And using it in the context of the steepest descent is beneficial since SD is notoriously known for being slow. Here is the core idea. In the original algorithm, we apply these iterations of updating alpha k to alpha k plus 1, where ek stands for the update direction to use. In the accelerated version of this algorithm, we update the current estimate alpha k as before, and keep this in a temporary vector dk. Then, we use an acceleration step that updates dk further by adding to it a vector proportional to the previous update direction, dk minus 1. This is said to be the vector alpha k plus 1. Observe that if we choose the parameter m to be 0, we get back to the original iterative scheme. We will typically choose m to be near 1. There are algorithms for setting this value automatically for best performance. We will not discuss them here. This acceleration idea is closely related to the conjugate gradient algorithm, which adds to its appeal.